Hello, my name is James Roback. I am the Director of Marketing and Sales for Utica Dental Lab. This is a recording of a presentation originally given in February 2020 to the Scranton, Pennsylvania Dental Society. In it, I speak about a brief history of fixed restorations and how our lab is adjusting to new advances in Zirconia technology. Additionally, I'll also share our triple model process that has helped us to reduce remakes and increase accuracy. So to get right into it, the presentation will cover an introduction of the lab, including a description of its capabilities. I'll then speak to the differences in fixed restoration approaches from the lab's perspective, a side-by-side comparison of lithium disilicate versus zirconia, and finally, how our method differs from other labs. Utica Dental Lab was founded in 1954 by Julius Wiegand. We began as a strictly removable lab, taking vulcanized rubber dentures and replacing them with acrylic. Matt Wiegand, Julius's grandson, is the current head of operations. He joined the lab in a full capacity in 2008. In 2010, we moved into a new modern facility right in downtown Utica on Genesee Street. 2 years later, Matt absorbed a fixed lab, Dentech, and began offering Crown and Bridge for the first time. Utica Dental Lab currently boasts 19 total employees, including 15 lab techs. Utica Dental Lab holds experience in very high regard, as it's the only way to guarantee a consistent product. As such, every lab tech working for UDL has at least 10 years experience. Rest assured your case is in capable hands, no matter the department, no matter the tech. So in chronological order, PFMs and PFZs. The first step, as always, is to pour a model. I'll expand a bit into how we are improving the modeling process later on in the presentation, but suffice to say, an accurate model is of critical import. Once a model is made, a coping can be created. A mold is casted in the case of PFMs. For PFZ, a Cad Cam coping is designed and milled. Once a coping is created, it is then degassed by firing in the oven. Then, 2 layers of opaque are applied, firing after each application. The porcelain body is added and sculpted to accommodate contact and tooth anatomy. After firing again, adjustments will likely need to be made to account for the expanding and contracting of the material. If needed, an additional layer of porcelain is added. Keep in mind that every additional layer added to a crown introduces new weak points. Each layer that's added to a PFM or PFZ can potentially cause the crown to cleave. This makes it very difficult to determine what the actual strength is and what the expected lifetime of each crown may be. The process also leaves a significant possibility for human error to be produced. Once size and contact is appropriated, the crown is stained and glazed. This slide will help you understand just how complicated the application of opaque and stain is. The process is highly laborious and very subjective to the skill level of your lab technician. Not only is the tech responsible for sculpting the shape, fit, and anatomy of the crown, but also is in complete control of the shade and color. An intricate knowledge of how various stains mix and react with each other is paramount to ensuring a lifelong restoration. Classic porcelain restorations are really a true artistry. What are some of the advantages of PFMs? Aesthetics mostly. If you have a lab that you trust who can supply top-notch porcelain work, then you won't find a more aesthetically pleasing restoration. The crowns are also very easy to adjust, easy to remove if necessary. The disadvantages? Well, they're the most time-consuming restoration. Since the process requires an application of layer after layer, and since firing is required between each layer, this makes the crown structurally weak compared to other solid restoration techniques. The process is also non-replicable. Any remake means starting from scratch as opposed to reloading a Cad Cam design, and of course, the quality of work is highly skill dependent. I know it is sometimes hard to consider the inner workings of our lab, but if your lab tech is sick or retires, the replacement is highly unlikely to be as skilled. Even in less obvious terms, imagine the quality of work produced on the Monday after the Super Bowl or Memorial Day weekend. it probably won't be the same as a normal mid-October weekday. The next major restoration labs begin to implement is the Emacs press lithium disilicate restoration. This is a very common restoration for anterior teeth especially. The crown is a solid unit which gives it better flexural strength than porcelain and a translucency that up until this point has been considered superior to zirconia. The process still involves casting a mold, so once again there is still some room for human error. The process begins with a poured model. A wax replica of the restoration is made by hand. Then the wax is invested and fired to create a cast. Once the cast is made, the lithium disilicate cylinder is loaded, heated to a liquid state, and pressed into the mold. Once cooled, the resulting unit is cut away from the cast, freed from any support struts, shaped and polished before being glazed and stained. This slide allows a close examination of the casting process. The cross-section of the cast mold in the third image shows the cast before the lithium disilicate cylinder is loaded and after the sintering process is complete. Before the lithium disilicate can be pressed into the mold, it must first be loaded into the top of the vacant mold, and then a plunger is oriented above it. Once the cylinder is heated to the point of becoming molten, the plunger is pressed down and the now liquid material is pressed into the mold. Once cooled, the lithium disilicate mold can be shaped, polished, and finished. This video shows a short portion of an Emacs tutorial video. In it is visible how the material is pressed down into the mold. The advantages of the press method are mostly regarding the aesthetics. For most of modern dental history, it was regarded that lithium disilicate exhibited superior translucency to zirconia, but inferior strength. However, compared to the PFM, the flexural strength is much improved. They are also less work intensive than any porcelain fused to metal. Some disadvantages are that a wax up and casting process still introduces a possibility for human error. The process also involves multiple firing and sintering steps, which take time. Also, the investing volume is limited. Most labs, depending on their size, can only press 4 to 5 units per run. This puts further time constraints on your restoration process. This in turn will place more strain on the production, especially in regards to quality control. Reproducibility is also a factor. If a crown fails an internal quality standard, you'll have to repeat the entire process from wax up on. Keep in mind that the best way to ensure quality is to remove human error and to find ways to give yourself extra time to fix any potential problems. It will become more clear how a Cad Cam process helps in both of those regards when we discuss our method in more detail. It is worth mentioning that Ivoclar has developed a Cad Cam Mill Process for their lithium disilicate restorations. This process will help eliminate the human error associated with wax up and investing. The Cad Cam process is similar to our zirconia procedure. The Cad Cam zirconia process is relatively simple compared to the previous methods. Once again, a model of your doctor's impressions are made. The models are then scanned via a benchtop scanner. Once the scan is complete, a crown is designed with our own design software. The design is then sent to our mill, and our milling machine begins milling the zirconia puck. After milling, the zirconia crown is sintered, then finished, glazed, and stained. We will get to some more detailed procedural information momentarily, but for now, the advantages of zirconia include an improvement in turnaround time. Designing a crown on computer software takes roughly 20 minutes. Milling a single unit takes about another 20 minutes. From there, we can sinter about 50 single unit crowns per session. This allows us plenty of flexibility to account for quality control. Having a digital file on record makes remakes manageable if there are any internal quality failures. Flexural Strength is the best in the market by far. Additionally, lab techs are much more easily trained in crown design, as opposed to the skills gathered over the years when stacking porcelain. One of the obvious disadvantages has been translucency. However, this metric is beginning to change. At least traditionally, zirconia lacks the translucency that lithium disilicate has to allow the types of aesthetics necessary for anterior crowns. We'll see in a moment that major advancements have been made in the multi-layered zirconia that are turning those assumptions on their head. An unfortunate disadvantage of zirconia is that the high flexural strength makes them very difficult to adjust and very difficult to drill or trim or shape. For the most part, your zirconia crown is going to be as you receive it. So up until this point, as a direct comparison, we all followed this general theory. Emacs crowns have a high translucency and high aesthetics, perfect for anterior crowns. Bruxer zirconia, superior flexural strength, and should be used for posterior crowns. Here I have presented for you some data from a 2017 study in the Journal of General Dentistry that compared translucency of various zirconias compared to a lithium disilicate standard. It largely falls into what you would expect, with lithium disilicate e.Max possessing the best translucency on a 1-to-1 basis. However, the Emacs has some limitations based on their flexural strength. These limitations affect the thickness of the restoration. The minimum thickness for lithium disilicate is 1 millimeter, while the minimum thickness of zirconia is only 0.4 millimeters. Taking this information into account paints a vastly different story. The translucency of many multi-layered shaded zirconia types are superior to lithium disilicate when compared at a practical level. Flexural strength was also measured in the study. According to this data, zirconia significantly outperforms lithium disilicate in flexural strength. This is a quick breakdown of how the three restorative methods compare. Translucency, as we saw with the study from the Journal of General Dentistry, has zirconia at 4 millimeters, on par with lithium disilicate. Zirconia can be considered superior in flexural strength, turnaround times, and reproducibility. In my opinion, the advancements in shaded zirconia have taken a structurally and procedurally superior product and improved on its weakest area. There will always be preferences in aesthetics, but with improved translucency, I believe zirconia to be a superior material for both anterior and posterior restorations. So let's talk a little bit about our process and how it may differ from other labs' modeling procedures. Your standard lab procedure goes a little like this. First, you prepare your impressions and pour your models. Then, assuming you are working in a Cad Cam method, you will prepare your models for scan. Once scanned, you will design the crown, mill, sinter, and finish. Our process mainly differs in the modeling process. The first major difference is that we did away with your classic pin models. The reasoning for this is twofold. Firstly, when you make a pin model, you need to section the model. When the model is sectioned, a lab tech needs to physically cut away the model. Depending on the patient's anatomy, it's possible that you can lose critical parts of information from the model. It may not be much, but a difference of only a few millimeters can lead to a larger mistake. Keep in mind that the purpose of making changes to your procedures are to improve the quality. The best way to improve quality is to remove the chance for human error. Decreasing the physical involvement of your employees in your work will help decrease human error. The other reason that we removed pinned models has to do with how the models are scanned into the design software. The modeling method that we are using to replace pin models is designed to optimize the accuracy of our scans. So we developed the triple model process. This process has helped improve accuracy and reduced remake percentages. The triple model process was designed to improve quality and decrease total materials used. In this process, 3 models are made: a die-cast model, working model, and a posing model. Each model is individually scanned into the program. Once the models have been scanned, the model is hand articulated and held in place with wax. That model is also scanned. These 4 scans are then used to maintain proper orientation while the crown is designed. Once the crown is designed, the 4 models can be overlaid and a check can be made accurately. Once the crown is milled, it is fitted on the working model and re-articulated. When you receive your case, you will receive the model unarticulated. We believe that by hand articulating the final crown, as opposed to having a static model, our lab techs will be able to constantly check the quality of fit and contacts. The beauty of the triple model process is that once the model is poured and articulated, all of the work is done digitally. This will decrease the chance of human error and increase accuracy. In addition, the process will speed up workflow and reduce materials. Each case has a record of each scan on file in the case any quality control failure occurs.